Hello guys and welcome to episode 2 of Escape the CAD Overlords series. Now today we will be talking about finite element analysis. It's a big one today, so come join me. So let's start by creating a model here. And let's say we will have, let's say we made a bracket, right? A bracket that potentially bolts onto a wall, right? So this is the back of the bracket. Let's make that 2 millimeters, and then in the center of it, we'll make a square tube. The square tubes on the outside have a fillet which is twice their thickness. This is going to be a 20 by 20 by 1 millimeter thick square tube. So I will be making 2 millimeter fillets around the outside, and then I'll be thin extruding it. Now you see that as I made the fillets, this turned orange again. Orange means that the magnitude is undefined. The position is undefined, and you can see that these elements are defined in relation to each other. They're not defined in relation to the origin, so I'll just put in the 3-point midpoint constraints that got broken, and we're back in business. So now I will thin extrude. That was a keyboard shortcut, but the command is over here. I do want 1 millimeter. If I wanted more, I would change it from here. Okay, I want 1 millimeter. And let's give that a length of 100. And then let's start the whole wizard, and I'll put in a couple of holes here. I want to make them M3 countersink clearance. Cool. In and edit the sketch. The reason I go into the whole wizard and then come out and go back in to edit the sketch is once in the whole wizard, it automatically goes back to adding holes. So you might think you have a constraint active, click somewhere and you get another hole. You don't really like that, so that's how I work around it. So let's make these two vertical and vertical to this as well. And then midpoint constraint with 3 points means that these are now symmetric this way. And I'll just say that this is like 12 millimeters from the top. And then I end the sketch. And this is the part on which I'm going to conduct my FEA study. Now, it is very often that we simplify a part that we want to study in finite element analysis. And this is what I've done here on purpose, right? Not as a second step. So in reality, this is not one part, it is 2 parts, and it would be welded together. So it would have a weld bit here and here on the bottom, a fillet weld. Now, I haven't done that, and I've made it one part, which means that this connection will not be able to fail in finite element analysis. So I won't get any data on whether my weld is strong enough. I could have done that. There are ways in finite element analysis to check for the strength of a weld, but we're going to be doing a much simpler example. This series is more like a proof of concept, a proof that yes, it can be done, and that's about it. So with that being said, let's save this. I'll save it in the FEA example folder. I'll say this is a square cube bracket. You will notice I'm not using spaces in the name. That's on purpose. I'll now export it as a step file. We're in FreeCAD, right? And we opened up this step file, and here it is. It's coming as a solid. That's what that little cube means. And we click in the FEM workbench, and we can start working. But I want to show you something. And here comes a bit of a rant too. Well, it's not a rant, it's an opinion, so it's even worse. This is where we set up our simulation, right? So let's check what options are available, because there's a point to be made here. Material for solid, material for fluid, I wonder what that's for. Non-linear mechanical materials. Reinforced materials like concrete. Here's the kicker. Fluid section for 1D flow. Electromagnetic boundary conditions. Flow boundary conditions and pressure boundary conditions. Guys, the FEM workbench in FreeCAD can do stress analysis, can do CFD, fluid analysis, and it can also do electromagnetic simulation. Plus, if you go to Tools and the Add-on Manager, and let's search for OpenFoam, CFD OpenFoam. Guys, this is, again, an amazing workbench. That's how I do CFD, by the way, right? It's an amazing workbench to do CFD with. Fully featured, very capable. OpenFoam has amazing support. Great forums for a professional like me, right, who runs a small freelancing company. There is no argument to be paying tens of thousands of dollars every year potentially to be buying these tools from ANSYS or SpaceClaim. They're the same company, I think, but anyway, from these large computer-aided engineering companies. Autodesk has a suite as well, right, and it's bloody expensive. It's for work, so I don't mind putting in more work to be adequately rewarded for it. Why isn't it the same for parametric design? Because Alibre is a perpetual license and it is very cheap. Alibre Atom, I think, is, and you can correct me if I'm wrong, is around 300 euros in Europe, which for a commercially usable parametric CAD system, I mean, it's a lot more powerful than FreeCAD, especially when you start talking about assemblies and drawings. And Alibre Design Expert, which has everything, global parameters, scripting, whatever you want to do with it, it's 2,500, right? 2,500 is about a fifth of what a SolidWorks license costs. So Alibre is where I would go for design, but for everything else, FreeCAD. And I acknowledge that they're doing an amazing job with it, and I will urge you to show your support to them. These guys, they need it, and they deserve it, right? So let's jump in the analysis right now. So the first thing you do is you click here and you make an analysis container, which right now is empty. First thing I do after that is I add a solver. We will add the Calculix solver, right, which is by clicking this S, but you can also add other solvers, which I haven't tried, right? Calculix solver has its limitations in parts with wildly different proportions, like very thin and huge area and stuff like that. But for the work I've been doing, this is good enough. And if you get stuck with it, and it's a multi-million-dollar project, well, by all means, pay ANSYS. So we added the solver. Next, we will be adding a material, and this is where the strangeness starts with FreeCAD. So I will add this ST37. That's an old DIN designation for low carbon structural steel. It has a tensile strength of 350 to 370 megaPa, and it's got a yield strength of 210 megaPa. What these mean, because we will be taking a look at numbers later on, 210 megaPa, after that it plastically deforms, and 350 megapascals, after that it breaks. So tensile strength is where it breaks, yield strength is where it plastically deforms. Stays that forever, right? So where can you find this? Because now it's in the recent folder. You go to standard and you go to metal and you go to steel, which has all these different types of steel. And there it is, ST37. By the way, this is the same one as this S235JR, right? It's the same steel. This is just the old DIN designation. Okay, so I selected it. Now I click this to retract that list, and I see that these properties here are populated. If they're not populated, you have the wrong material, which is entirely possible because you have this appearance folder. If you click anything from here, it doesn't have the mechanical properties populated, so it's not going to be much use for you. So we'll add the geometry to the material, right? We will tell FreeCAD which geometry has that material. And this is a very important step. This needs to be exactly the same geometry as the mesh. So we will do a bit of a, what I call a rain dance here, right? We need to go through the motions exactly. So first of all, we tell it that we'll be giving it a solid. Then we click add. We click add first. That's true for all of the menus in FreeCAD. We click add, and then we click on this side surface. And it's picked up port feature solid 1. So we're good here, and we'll click OK. We've got the material in. Now we want to create the mesh that we'll be using for our simulation. I click on the same surface. I can click on the tree, but no, I will click on the same surface. Now these two buttons become available. I can either create a mesh with NetGen, or I can create a mesh with Gmesh. Now Gmesh has a lot more options, and for elaborate designs it's probably more reliable, but for simple stuff NetGen is, I think, a bit quicker. And I will make the mesh now, and I will probably hit a wall with it not work, and because I do want to make a point. So I had this selected. I click on the N button. If this wasn't selected, the button would have been grayed out. And I'm not going to change anything here, right? And I'll hit apply. And I'll think for a minute. Let me note here that when working with meshes for finite element analysis, you usually want large meshes. And large meshes are very, very heavy for your computer, right? So with the moderate setting for the fineness, I got 138,000 nodes. Okay, I'll hit OK, and this will get locked in. And you see, even hitting OK takes a bit of time, right? Okay, cool. Now I will hit this little eye and hide my mesh, and I'll show my model again, because now we'll be adding constraints and loads, and you can only do that in the original model. You cannot do that in the mesh. So I will start with this. This is a locked constraint, right? You also have this, which is a rigid body constraint, and you can do so much with it. You can be very precise about it. But for now, what I want to do is I want to completely lock a couple of surfaces. So we click add first, and I will lock this surface. Then I will lock this surface. Okay, so these are the icons you see there. Obviously, I did not need surface face 27, so how do I remove it? I click add to stop the add command, and then I click remove, and I remove this face. We added the locks that we wanted to add, and then I will now apply a force load. Again, we click add first, hit on the surface. That's not the direction I want. I reverse the direction, and I will add it with 20 kilograms, right? Now 20 kilograms is 20 newtons times the acceleration of gravity. So it's just below 200, but you know, no problem in adding a bit more of force. It's something like an extra safety factor applied in the loads of the study already. So I'll hit OK. I can now turn my body off and show my mesh again. So I've got my mesh, I've got my materials, and I've got my constraints and my forces. So now I will double click on my solver, and I will select what sort of analysis I want to do. I want to do an analysis study. There is a buckling study you can do. For example, in Fusion 360, you can do a buckling study, and it's behind the paywall, right? So I will do a static analysis, and first thing you do is you need to write the input file. That's what the .inp is, and we got an error. The error says only one material object, but this one has a reference shape, and the reference shape will be ignored. FreeCAD weirdness. Sometimes the analysis won't work until this goes away, and sometimes the analysis will work with it. And in this particular case, I'm pretty sure the analysis will work even with that error, although it will error out this time. And I ran Calculix, and around the 3.6 second mark, this is too quick, right? It couldn't have produced results. It errored out. Nodes but no results found in FRD files. It means there is only a mesh but no results. In any case, what happened here? So we've got large dimensions like 80, 100, whatnot, and we have small thicknesses. In cases like this, you need to go for a finer mesh, right? And I won't get into the nitty-gritty here, but I'll double click on my mesh item here, right? And I'll go for a finer mesh. We were at 138,500 nodes. So I'll hit apply and let's see where we end up with the fine mesh. And this is taking longer, and it'll take considerably longer time. Okay, another error, BFGS update error 2. And that error was thrown, who knows, error. But we did successfully refine the mesh, and it is now 330,000 nodes. So the matrix, right, because this is linear algebra, the matrix for the nodes is 330,518 by 330,518. It's a lot of numbers. I'll hit OK. I need to delete these old results that had errored out. I will do it as soon as the mesh gets locked in. Guys, finite element analysis is no toy, right? It's not a game. You see that BFG update again. I'll just ignore it. So as I was saying, this is no game. I'll write the INP file again. This is a Ryzen 7 laptop, 5800H processor, 8 cores, 16 logical processors, 32 gigs of RAM, and a 3060 NVIDIA card, right? Again, error is thrown. And you can see how much it's being bogged down by a relatively simple part, right? Finite element analysis, you need some serious computing power. Alibre can run on a relative potato, actually, especially for parts like this, but finite element analysis, you need serious horsepower. So let's see if refining the mesh up to 330,000 nodes will make this simulation run. And it's a good thing we went past the first 5 seconds, because that's where the initial checks happen. We've got the timer here, and I expect it to take a while. And we have results. Calculex done without error. That's 2.5 minutes, over 2.5 minutes. If I wasn't recording this would have been faster. A good SSD also helps with finite element analysis, because it's always writing results on the disk and whatnot. But we finally have our results, and I will now close the solver because I won't be able to see the results with the solver open. And I select CCX results, and after a few moments this option should be available, and I will click it, and I will get the results page. So here are all of the results type that we can get. I'll go straight for phone misses stress. Okay, so I clicked on the phone misses stress, and I get some numbers here. I get that the minimum value is 19.05 kilopascals. That's nothing for steel, toying with it. And the maximum is 332 megapascals. Now, we said that this material plastically deforms, so it deforms permanently after 210, and at 350 it'll break. So this can't be good, right? Let's think about it for a bit. First of all, let's show our displacement here. I will show my displacement with a factor of 50. Okay, there we go. Now this gray surface, if I hide this pipeline CCX results, that gray surface should go away. Again, these are some hardcore stuff, guys. Okay, we're really pushing the material, the computer here. So this is finite element analysis. We've got a range, right? Green is good, red is bad. where's that high load, right? Well, if we zoom in over here, you'll see that near this very sharp 90-degree edge, we've got all of our transition from green to yellow to red. So this is where these 330 megapascal loads appear, only here in these sharp edges, which a sharp edge is a stress concentration point, right? This is very well shown by our analysis, but there's another problem, right? When you have very fine meshes in finite element analysis, near these sharp edges, especially if you've got torsional loads going through them, you get singularities, right? You get stuff being divided by other stuff that, tend towards zero, and you get numbers that are not real. So if this was, a job that I took, right, what would I say? Can this 20 by 20 by 1 millimeter thick tube handle 20 kilograms? Well, we will click here where it says histogram. Now this is the histogram of all of the values, all of the von Mises stress for every node. Okay, you see that we've got over 120,000 nodes showing from anywhere from 0 to 10 megapascals. And you can see that after, 100 megapascal, this drops, very sharply. And after, 130 megapascal, we can't even see the values. Well, if you click up here and you manipulate the axis a bit and say that the maximum value for the y-axis is 50, let's click OK. Well, now you see that, like, we zoomed in, right? We zoomed in near the x-axis alone, and you'll see that there are nodes that report higher values. Here's our 338. This is definitely an outlier, right? But how about these? Well, I'll tell you what. If it's under 50 nodes at 330,000 that are reporting a value, you can safely ignore it. And I'll give you another one. In Fusion, for example, you might not have even gotten that result, that 338, because it has got a lot of empirical equations, a lot of real-world filters, if you will, that take out these values, these outliers. So you wouldn't have gotten this value. You would have gotten potentially the 200 megapascals one. Let's see if we take this up to 100, what will we see? And yeah, 200. So there's a very, very sharp drop, I would say, after, what is this? Like 50, 60, 70, 180 megapascals. It drops really sharply. So I would be inclined to say that the real value for the stress, right, the one that I should be worried about as an engineer, is somewhere around the 160 megapascals range. Now, what would that tell me? Well, that would tell me that, for example, this very part in particular would handle the 20 kilogram load for a few times, but not forever, right? So few technical data still as a fatigue curve that as steel fatigues, its strengths fall roughly to half. So if I wanted this to, last for a lifetime, I need to change it, use a thicker tube, and make sure that these real stress nodes do not show stresses over 100 megapascal. So if this shows 160 megapascals of stress, right? If you have the stress fatigue curve of your material, you know exactly how many cycles it will take before plastically deforming, so you can gauge if that material is good enough for your application. But anyway, so that's how you can do finite element analysis in FreeCAD for parts that you have designed in Alibre. This is just a proof of concept, proves that you can do it. Let's go for displacement magnitude. Yeah, there's some color. Displacement, it's the red is the part that has moved from its original position the most. So this proves that you can do finite element analysis, that is with FreeCAD, and you can do so much more. And if you want a video where I show you how you can get even more detailed results per node or whatever using ParaView, let me know. Or even if you want to do topology optimization, yes, that thing that you pay thousands of dollars for in SolidWorks and Fusion. If you want me to show you how to do topology optimization for free with FreeCAD using your intelligence, YI instead of AI, yeah, I'd be happy to do a video on that too. And with that, I hope you enjoyed it. Hit like if you liked it. Hit subscribe if you really liked it and you want more. And I'll catch you in the next one.